Great. Let's keep on talking then about Euler circuits and Euler paths. I will refresh our memory just about the terminology here. An Euler circuit uses each edge once, exactly one time. It covers all the edges without repeating any of the edges. That's called an Euler circuit. And it's a circuit, meaning it comes back to where it started. An Euler path also uses each edge one time. But it's a path, right? So this one, circuit, means circuit starts and ends at the same point. Whereas an Euler path does not do that. It starts at one vertex and ends at a different one. Euler circuit starts and ends at the same vertex. Path does not start and end at the same vertex. All right? And the important thing that we talked about last time is how do you know if there is an Euler circuit or an Euler path? And the way you know is by looking at the degrees. So if all the degrees are even, then an Euler circuit exists. And if all the degrees are even except for there are two odds, then an Euler path exists. So if all are even except two odds, then then an Euler path exists. This is how you tell if these things exist or not. It's very easy to check, the degree. You just look at all the degrees, how many edges touch each vertex. And that's all it takes to tell if the Euler circuit or Euler path exists. All right? Great. I just want to do some examples today and maybe talk a little bit about, the next big question is, if you know it exists, then how do you find where it is? And that's a different matter. But the theorems that we talked about last time are about when it exists or not. I should just say the Euler path exists and it starts and ends at the odds. All right, if you have exactly two odd vertices, then an Euler path will exist in that graph. And those two odd ones are the places where it starts and where it finishes. Okay, let's just look at a few examples. How about I got a graph like this. All right, let's say these are like streets in a little neighborhood. Someone got a text. Streets in the neighborhood, right? And let's say that we want to plow the streets. How about that? Mr. Plow wants to plow the streets. That's what he does, right? Wants the plow. I meant to write to plow. So the question is, I don't know where he's going to start or whatever. Is it possible to go down each street once and end up where you started? So can we go down each street once without repeating any and finish where we started? This question that I'm asking is really just, is there an Euler circuit or not? And the answer is, well, you look at the degrees of each vertex. So I'm going to look carefully over here. You don't have to look too carefully. Can I just write in the degrees here? This one here is degree 2 because there are two edges which meet this vertex. So that's a 2. That's a 3 because there are 3 edges right there. That's a 2, a 3, a 3, a 2, a 3, and a 4 in the middle. All right? Those are all the degrees of the vertices here. So what's the answer to my question here?
No.
The answer is no. Right. You cannot do this because this would mean an Euler circuit because I said finish where we start. And this is not possible because I have some odd vertices over there, right? If you want to do this with an Euler circuit, they all have to be even, and they're not all even over there, all right? Could we do it with the Euler path? That is, even if Mr. Plow starts at one spot and finishes at another spot. Is that possible in this graph? No, even that is not possible. So I will say it's also not possible if we start and finish at different points. That would be an Euler path, which is also not possible because I see 4 odd vertices, right? Those are the important ones, the odd ones. And there's too many. If there were exactly 2, then that would be possible, but there's 4 of them, so that is not possible. Not possible if we start and end at different verts. All right? How about this? How about let's imagine that Mr. Plow's wife, Mr. Plow's girlfriend, is a road builder, Ms. Road. Is there a way that you could build a new road over here to make this possible for Mr. Plow to do that? She's a supportive wife to her dear husband. I'm going to try and copy this here. Can we add a new road in there which will make one or the other of these things possible? Anybody have an idea? Yeah.
Maybe like another curved road from 3 and 3 to the bottom, right?
Yeah, we want to somehow connect up 2 of the 3s. If you were to connect 2 of the 3s together, then actually, I think each of those 3s would like turn into a 4, right? And there's several ways you could do this. He said put in a curvy road down between these 2 3s. So they used to be 3s, right? But I'm going to insert another road. Now, he said curvy. I'll do like that, maybe. Doesn't matter if it's curvy or not, right? But Ms. Road, she likes the curves. Okay, now, what's the point of that, though? The point of that is those 2 3s are no longer 3s, right? That's why this is going to work. So that 3 is now a 4. That 3 is now a 4. And now we have 2 odds and the rest are evens. And so now it should be possible to start somewhere and cover every road and end somewhere else. So now there is an Euler path, right? You can do this now starting at one vertex, covering every road, and then finishing at another vertex. Can we just try and draw that in? Now, I usually draw mine in red so that's easy to see, but I know you all don't have reds, probably, when you're doing this. I'm going to try and draw in. Anybody have a suggestion? Where should I start?
Top middle.
The top middle, yeah, there's a rule, actually. You must start at one of the odds if this is going to work at all. So you could either start at the 3 on the top or the 3 on the side. Either one will work, but I'll start at the top just because he said so. While I'm drawing, just so that it's clear what I'm doing, I'm going to draw this. You got to be a little sloppy when you draw this. I'm going to miss the original lines in the graph because if you draw right on top of the original lines on the graph, it will be impossible to tell what you're doing. All right, I'm just going to try and do this. I mean, we haven't really talked about how good strategies for doing this, but hopefully this is just going to work out. Now, I'm starting at one of the odds. My plan is, and the only way this is going to work is if you start at one of the odds and end at the other odd. So don't go back here right away. I'm going to try and cover this other stuff first. Maybe I'll come up this diagonal here, and then back down the windy road, like that. And then up the middle here, I hope I'm doing okay. Around the side, up here, down there. I like that. I think I did it. All right? When you're drawing these on your homework or something, please don't try and draw right on top of the original graph lines. If you tried to do that, it would look something like, actually that's the same graph, isn't it? If I just don't make the silly windy road. But check it out. Look how easy it is to tell if I draw right on top of the graph like this. How about this, and then this, and then this, and then this, and then this. What am I doing down here? Sometimes people are like, oh, can't I just like put arrows on all the edges? The answer is no, not really. It's not clear at all what you're doing here. For instance, okay, you start here, but I have an arrow going out that way and also an arrow going down that way. So it's already not clear to me which direction your path is supposed to go from where you start. So don't draw it like that, please. Draw it like this. It might look a little messy, but it makes sense. All right, any thoughts about that? This is a cute little Mr. Plow example. All right, great. I got a few more cute little examples. Here is another one. This one, you'll just have to look at my screen. Check it out. This is the standard Pacman level. Remember Pacman? Pacman was a video game. I don't know if you're familiar with Pacman. One of the most beloved video game characters. Maybe one of the first actual characters. Not much of a character. Anyway, the idea is Pacman is this little thing here. These are the bad guys. And your goal is to eat all of the little dots. You just sort of walk around. There's no buttons or anything. You just walk around, eat all the dots. And when you eat all the dots, then you win and you go to the next level, which is the same as this again, only it's they go faster. Anyway, the natural question, and I'm sure everybody, when they're playing Pacman, is natural to wonder, can I do this without ever retracing any steps? Run around eating the dots and never go back across an area where I already ate the dots? Actually, you can answer this question in terms of Euler circuits. If I imagine this whole thing, I'm going to try and imagine it is a graph. So there's Pacman right there. You know, on your first, when it starts, you immediately either go this way or you go that way. So I'm going to think of this as just a big graph with all of the possible places where the Pacman can walk, right? And it looks something like this. And my question is, can you actually do this whole thing, eat all the dots, without ever retracing your steps? Now, retracing your steps, whoa, sorry. It's a bogus line right there. Right? I'm trying to just think of this as a graph. And the Pacman, you could walk down here also, right? You could walk there. All right, and you can also walk off the side here and come back over there, which is hard to draw, although actually it's not really hard to draw. Actually, now I don't even need this original picture anymore. Oh no. Why did that happen? I thought I could delete the image. I guess not. I thought I was drawing on. All right. Here's how you can do this as a graph. Really, this is like this, right? Right. I just added an extra edge. Now, when you're actually playing this, you don't see Pacman like float up here and go around. But in terms of a graph, this is equivalent to going off the side and coming back on the other side. All right. Anyway, the question here really is there an Euler path, right? Because I'm asking you about, can you actually cover all of this business without ever retracing your steps? What do you say? Is it possible? In this, all of these red lines. Oh, maybe I can do this. Can I grab the red lines? Oh, yes. This is what I wanted to do before. And it looks like I missed a part of it. Like that. Can you do an Euler circuit or an Euler path in here? It has to do with the degrees, right? That's the only thing that you really have to worry about is the degrees. Are all the degrees even? I don't think so, right? I mean, you can look. Was it? Just look at the degrees here. Like that's a 4, that's a 2, a 2, a 2, that's a 3. Are there any other 3s? Yeah, actually, there's a lot of 3s. All of those 3s are the ones that really matter in terms of answering this question. There are many odd degree vertices in there, which means there is no Euler circuit, and there's also no Euler path. Euler path would be if there were only 2 odds and the rest were evens. I assume that the designers of Pacman intended for this. I think the game is more interesting if it forces you to walk back across somewhere you've already been, rather than there just being some kind of best way to do it. There really isn't a best way to do it in Pacman. You have to think on your toes, right? make the hard decisions, the hard Pacman decisions. So this has no Euler circuit. I didn't write in all the degrees, but all you care about is, are they all evens or not? There's many odds in this case. No Euler circuit or path, which means in the game of Pacman, you must retrace your steps sometimes in order to finish the level. All right, a fun little fact there. Amaze your friends. Any thoughts about that? All right, I got another one. How about, this is another sort of real world example. These are real world examples, although I'm not sure how useful the knowledge is. I suppose that's useful knowledge if you're a competitive Pacman player. Here are the standard lines on a basketball court, not baseball. I know that much about sports. I don't know a lot about sports. I can tell the difference though. Let's imagine you're the gentleman who paints the lines on the basketball court. And the question is, can you paint all the lines with your line painting machine without retracing over one of the lines you already painted? All right, it's the same kind of question, and it has the same kind of answer. You consider this whole thing as a graph. So the question is, can we paint the lines? I imagine, I've never seen them paint the lines, but I imagine there's some kind of a machine you push around that shoots paint out the bottom. Can you just like turn the paint gun on and just push yourself around the whole way and paint all those lines without ever retracing? Can we paint the lines without retracing? What do you say, yes or no? The answer is no. Again, it has to do with looking at the intersections and the degrees at each of those intersections. And are they all evens? And the answer is no, they're not all evens. Like right here is a 3. Here's another 3. Now, if there are only 2 odds, then maybe you could do this by starting at one of the odds and finishing at the other. But there are not only 2 odds. There's many odds, right? This is a 3. This is a 3. These are all 3s. So you definitely cannot do this without retracing. The answer is no. All right? More useful real-world mathematics. I don't know how useful this is. Although, I mean, I suppose there are people in the world for whom this is useful. Those people are not you and me, I assume. But it is a useful question for somebody. And let's be honest, that's like most of the math that you've learned in high school, say, is not per se useful in your life every day, but it is useful to somebody. And that's the point. That's when we say allegedly useful mathematics. That's usually what we're talking about. All right, any thoughts about that one? Great, I got some for you to try. These are more made-up examples, just so that they're easy to write down on a piece of paper. I have 3 graphs here. Your job each time is to tell me, is there an Euler circuit, or is there an Euler path, or is there neither? So my first one is a cute little star here with a circle around it. Does that make it satanic if I do that? Or upside down or something? I don't know. I'm also not an expert in satanic symbols. This is the Triforce. I'm an expert in that. But I'm actually, to make it more interesting, I'm going to add that thing on it, which kind of ruins it. And then I got one more here. So your job each time is to say, for each one, this is 3 separate ones, say, is there an Euler circuit? Is there an Euler path? Or neither? And if there is, then draw it in. See if you can draw the Euler circuit or the Euler path, if there is one. Draw it, if so. I'm going to walk around and see how you feel. All right. Okay. All right. You should be looking at the degrees. That's the important thing. All right.
This one I like. There's no arrows on it. There's arrows on it. Yeah, no. This one has no arrows. No, it does. Yeah.
Okay. All right, can we talk about these? I see some good progress here. What matters is the degrees. That's the important thing to look for in these pictures. So this one here, what are the degrees every time? I believe actually every degree in this one is 4. Remember, the way you decide this is how many edges are touching this vertex, and in this case it's 1, 2, 3, 4. Don't be fooled by this. This circle looks like it's kind of going straight through, which it sort of is, but it still counts. Each of these parts of that circle count separately in the degree. So it's 1, 2, 3, 4 edges touching that one. And these ones in the middle also have 4. They all have 4, right? Since they're all even, that means there is an Euler circuit. So this one has an Euler, can I say EC, an Euler circuit. All right? Can I draw it in there? Yeah, probably. You can start wherever you like, and you just have to never reuse an edge. Now, there is sort of a technique for doing this that we're going to talk about next time. We haven't really talked about it yet, so as for now, I would say just sort of try and make it up and hope that it works. So if I start here, maybe I'll go around the outside edge. Like I said, don't draw your lines right on top of the original lines, because then it'll be impossible for me to tell. And then maybe I'll just go around the star like the way that my mommy taught me how to make a star when I was a kid. Around here, I'm gonna cover all the edges, right? Down here and back up there. Finishing off right there. Isn't that cute? I think so. This is an Euler circuit. Any thoughts about that one? I hope you did something like that. Of course, there are many other ways that you could have drawn your circuit in there. You just have to hit every edge, and you can't repeat any. How about this one? Again, you look at the degrees. That's a 2, that's a 4, a 4, a 4, a 3, and a 2. So I see mostly evens except for 2 odds. That means that there is an Euler path. And to draw it in there, I'll say EP. To draw it in there, you better start at one of the odds and finish at the other odd. So maybe I'll start on this one. And again, I'm just going to try and do whatever and hope that it works. Come up here, up there. I guess I have to come back here. There we go. I think that worked out nicely. All right. That's an Euler path. Again, you could have drawn this in many different ways, but you better start at one of the threes and end at the other three. All right? Any thoughts about that? And then one last one. This one here, I think you should have said this one has no nothing. You can't do a circuit or a path in this one because there's too many odds. That's a 3. Down here is a 5, and these two corners are 3s. So I see 4 odds there. This means it's not possible to do an Euler circuit or a path. I believe the others are evens. That's a 2. This is a 6, and a 2. But that doesn't matter. I have too many odds. So this one has no Euler circuit or Euler path. Exclamation. All right. Any questions about those? It's pretty, once you know what to look for, it is not hard to decide. You just got to look at the degrees. All right. I got one more example. We have 10 minutes remaining, which will be plenty of time for one more example. This is a slightly more complicated example. This is about, let's say, the mailman, the walking mailman, walking around the block. Let's say this is a nice sort of rectangular city block with grid of, streets. And these are a bunch of buildings that people live in, or a bunch of neighborhoods that people live in. And let's say the people live at these dots, right? The mailman is walking. These are the streets, right? Walking these mean streets, and delivering the mail to these people who are the dots. The dots are the people that have to get mail. All right. I am drawing in the dots. No. And 2 more dots here. All right. So these are the streets. Let's say the mailman likes to stay on one side of the street. So some of these streets, the mailman will walk down twice because it's going to be, once on one side and once back the other side. But some of these streets, the mailman only wants to walk on once. For instance, right here, when the mailman goes on this street, they only have to do it once because there's only the people on the one side. All right. I want to see if we can analyze this. The same question as usual, although this time the question is not exactly can he do it without repeating the same street, because actually some of these streets we want to repeat. But can I just say, can the mailman or the mail carrier deliver all the mail without, can I just say, extra walking? Right? Some of these streets require 2 trips, and that's fine, but I don't want to do an extra trip anywhere where it's not necessary. All right? Can we answer that kind of question here? Like I said, this is a more complicated question just because it's not exactly obvious how to translate this into a simple question about Euler circuits or Euler paths. But here's the idea. I want to think of this. I'm going to sketch in a graph. First of all, a graph of the streets is the important thing because that's where the mailman is going, along the streets. Where exactly the dots are, it matters, but those are not, for instance, they're not vertices on the graph. I would say the graph that we're looking at is these streets. And in fact, only some of these streets matter. I think really only that, and I don't even care about that. All right? Those red ones there, those are the only streets that the mailman is interested in walking on at all, right? And so if you're going to translate this into a graph of the guy walking on the edges, those would be the ones. The mailman or woman, I don't mean to use gender-specific terminology. Those are the only streets that matter. And, like I said before, some of these we actually want to walk on twice, and some we want to walk on only once. But we can indicate that in the graph by just kind of doubling up those edges. So I'm going to make this into a graph. It has vertices here, 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 and here. And some of these edges, actually, we want to go on twice. So I'm going to do that by just like doubling them up. So those two, like right over here, I doubled this edge. That's because I know that the mailman actually wants to do this one twice. All right? Some of them, also this one here, the mailman actually wants to do this one twice. So I'm going to double that one up. And this one here. Any more need to be doubled up? I see somebody indicating with their fingers like this. Yeah, there's a vertical one on the end, which also needs to be traveled on twice. All right? Otherwise, all of these streets only want to go on once. All right? So the real graph that we're looking at here then, I'm just going to redraw it, is like this. And here. All right? So sometimes this is a tricky sort of initial step. Sometimes it takes some amount of effort to translate the original scenario into the graph that you're actually interested in looking at. But that's what it amounts to in this problem. This is the graph that we are actually interested in. And now we ask, on this graph, is it possible to do an Euler circuit or an Euler path? And we answer in the usual way by looking at the degrees. So the degrees here, that's a 2, right? That's a 2. That's a 3. I don't like the looks of a 3. This is a 3 also. This down here is a 4. I'm counting each time the number of edges that touch that vertex. This one in the middle is a 1, 2, 3, 4, 5. That's a 5. This is also a 5. All right? What's the answer to my question then? Can the mail carrier deliver this without extra walking? The answer is no. You're going to have to repeat some of these streets because I have too many odds here, right? There are 4 odds. That means no Euler circuit, no Euler path. So the answer to this question is no, unfortunately. All right? That's how we do it. And I think that'll do us for today. I hope you all have a good weekend. See you next time.